Hello everyone and welcome to the coronavirus edition of the first exercise from our signal theory class. This exercise will not be very complicated, mostly we will take a look at some problems with the complex exponential. The first problem is this: write the complex exponential with the complex amplitude 3 and complex frequency 5j and express its real and imaginary part. So, this is the formula for the complex exponential. This is the complex amplitude and this is the complex frequency. The complex amplitude is supposed to be 3 and the complex frequency is supposed to be 5j. So we just substitute and this is the required result. Now we can use the Euler formula and we can rewrite this complex number into this form. And here we can identify that this is the real part and this is the imaginary part. The next problem, do the same but for complex amplitude 3 plus 3j and complex frequency 2 plus 5j. So again, this is the formula for the complex exponential. Now this is the complex amplitude and this is the complex frequency. The only hitch here is that before you use this complex amplitude, you want to transform it into the polar form. Once you have this polar form of the amplitude, you can substitute it here. And also for the complex frequency, you will substitute this. When you do that, you will get this complex exponential. And here you can rearrange these exponentials so that you get this, and here you can use the Euler formula to obtain this form. And in this form you can clearly see the real and imaginary part. Now here I have another type of problems. I have some expressions with complex exponentials and I want to express them as real signals. So first, I have this signal, which is the difference between these two complex exponentials. And from the lecture, you should be able to identify that this you can write as a real signal sine of omega t. Another example, here I have this signal, which is the sum of these two complex exponentials. And again, from the lecture, you should be able to identify that this sum is equal to a real function, the cosine of omega t. Now, this problem. Here I have this sum of complex exponentials. What will that be equal to? Well, to analyze that, I will combine these two exponentials into a single exponential and these two exponentials into this single exponential. And here I can identify that this expression is essentially this expression, except I'm not dividing by 2, and instead of this omega t, I have omega t plus phi. So this expression will be equal to cosine, except it will be multiplied by 2, and in the argument I will add this phi. Now here I have this difference of two complex exponentials. How shall we deal with that? Well, if I have a difference here, that will probably lead to a sign, but for a sign I will need to divide by j, not multiplied by j. But that is easy, I just need to realize that j is equal to minus 1 over j. So I can rewrite this multiplication by j to the division by j, and I need to add this minus. When I do that, I can actually identify that this expression is similar to this one, except I don't have this division by 2 here, and instead of omega t, here I have omega t plus 6. So instead of omega t, this will be equal to minus 10 times sine omega t plus 6. Now another problem. Here I have a signal which is the sum of these two complex exponentials, where this s, the complex frequency, is equal to j omega, and this a, the complex amplitude, is equal to 5 times e to the j phi. Now, to solve this, you could just use the formula from the lecture, where I showed you that this expression is equal to this one. So you could just identify that the complex amplitude has magnitude of 5 and that you would substitute here. The real part of the complex frequency is 0, that you would substitute here. This omega is this and this phi is this. So from this expression you could directly write that the result is this. Now if you do not remember this formula, you can just take these values and substitute them here. That is what I have done here. Now I can just rearrange this expression into this form, and here I can identify that this is actually a cosine of omega t plus phi. So the result will be 5 times cosine of omega t plus phi. In this slide, I will continue with similar problems. I will have some signals composed of complex exponentials, and I will want to express them as real signals. So here I have a signal that is composed of a sum of two complex exponentials. This time the complex frequency is -2 plus j3, and the complex amplitude is 2 times minus 2j. The fastest way how to write this sum of complex exponentials as a real signal is to convert this complex amplitude into the polar form, and then you can use the formula that I derived for you during the lecture. Here I can identify that the magnitude of the complex amplitude is 2 times square root of 2. That will come here. Here I can identify that the phase of the complex amplitude is minus pi over 4. That will come here. Here you can identify that the angular frequency is 3. That will come here. And last, here you can identify that the real part of the complex frequency, that sigma, is -2, so that will come here. And from that you can immediately write this result. You can also derive this result in smaller steps. Basically, all you need to do is to take this complex frequency and this complex amplitude, ideally in the polar form, and substitute them into this expression. That is what I have done here. In this expression, you will need to break this exponential into two exponentials and this exponential into these two exponentials. Then you will combine this exponential and this exponential into this exponential, and this exponential and this exponential into this exponential. That will leave you with this expression. And in this expression, you can collect 2 times square root of 2 times e to the minus t. When you do that, you will get this. Here, you can identify that the expression in the bracket is actually 2 times cosine of this argument. Consequently, the final result will be this. Alternatively, you can solve this problem in a different manner that will give you the same result but expressed in a different form. What you can do is to keep this complex amplitude in the rectangular form and substitute that rectangular form in here and here. When you do that, you will get this. Here you can distribute this multiplication and this multiplication. That will give you this long expression. In this long expression, you can break this exponential into two exponentials, this exponential into two exponentials, and so on and so forth. Then you can collect e to the minus 2, which occurs in each of these expressions. You can also collect this number 2, which is in each of these expressions, and in this expression and in this expression you can collect j. When you do that, you will get this expression. And here you can identify that this bracket actually corresponds to 2 times cosine of 3t, and this expression actually corresponds to 2 times the sine of 3t. So you can rewrite this in this form, which you can also write like this. So this sum of complex exponentials you can rewrite as a real signal in this form and also in this form. Both these forms are the same. And this also means that you can write a cosine with some general non-zero phase as a sum of a cosine with zero phase and a sine also with a zero phase. Let me repeat that. You can take a cosine with a general non-zero phase and you can write it as a sum of a cosine with zero phase and a sine also with a zero phase. This fact we will use a little bit, so here I will present it once more in a slightly more general form. Now this time my signal will be this sum of complex exponentials. Now the complex frequency will be j times omega, and my complex amplitude will be a plus jb, which I can also write in this polar form where the magnitude is given like this and the phase is given like this. Now, similarly to the previous problem, I can take this complex amplitude and this complex frequency and substitute them here, 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 and here. When I do that, I will get this. In this expression, I can combine these two exponentials into a single exponential and these two exponentials into this single exponential. That will allow me to rewrite this expression into this form. And in this form, I can easily identify that this is equal to this cosine. Now the alternative approach. I will use this rectangular form of the complex amplitude and I will substitute that into this expression. That will give me this. Here I will distribute this multiplication and this multiplication, which will give me this long expression. In this long expression, I can combine these two exponentials like this and these two exponentials like this. And here I can identify that this expression is equal to a cosine of omega t and this expression is equal to a sine of omega t. So I can write this entire expression in this form. So this combination of two complex exponentials I can write both in this form and in this form. So again, I can write a cosine with some non-zero general phase as a sum of a cosine and a sine, both with zero phase. Moreover, here I can see that this constant a and this constant b are real and imaginary part of the complex amplitude of these two exponentials. So if I want to rewrite this expression into this form, I just need to compute the magnitude like this, the phase like this, and that will give me my result. And if somebody is still not bored to death, I can definitely finish you off by showing you the equivalence between this expression and this expression using the formula of a cosine of a sum of two angles. So in this expression, I have a cosine of sum of two angles. This would be the first angle and this would be the second angle. From the high school, you should know that the cosine of this sum can be written like this. And this expression I can rewrite into this form. Here I can identify that this is actually the real part of my complex amplitude, that is A, and this is actually the imaginary part of my complex amplitude, that is B. Now let me show you this graphically. Here, this blue line is a cosine, specifically it is a cosine with amplitude of 3. And this red line is a sine, specifically it is a sine with amplitude of 4. Now when I add this cosine and this sine, I will get this, which I have plotted here using the green line. This is the sum of the cosine and the sine. Also, I can express this sum using this form and these formulas, which I have done here, and I have plotted the result with this dashed line. And you can see that the dashed line exactly corresponds to the green line. So this form and this form, they are equivalent. The moral of the story here is that I can combine a cosine and a sine with some general amplitudes, and that will give me a general cosine with some general amplitude and some general phase. Or vice versa, I can write some general cosine with some amplitude and some phase as a sum of a cosine and a sine with properly chosen amplitudes. In this slide, we will continue the gymnastics with the complex exponential. I will give you some expressions with sines and cosines, and I will ask you to express them as complex exponentials and find their complex amplitudes and complex frequencies. This is the first problem. So here you have a signal which is a sum of a cosine and a sine, and I would like you to express this as a complex exponential. To do that, you need to remember this formula which I showed you on the lecture, and then you can identify that this expression actually corresponds to this one. this number 3 would correspond to this magnitude. This sigma would be 0 because I do not have any real exponential here and here. Then this number 4 and this number 4 would correspond to this angular frequency omega, and this number 5 would correspond to this phase. And from the lecture I know that this expression I can write as a complex exponential in this form. So now that I have identified these individual variables, I can write this expression in this form. And here I can identify that this is the complex amplitude. My complex amplitude is this, and J times 4 is the complex frequency. This is my complex frequency. Okay, now this problem. This expression is actually almost the same as this one, except I have added this real exponential here. So whilst I had cosine and sine here, I have a damped cosine and damped sine here. So pretty much everything will be the same as before, except now this sigma is -2. So I can write this expression in this form. The complex amplitude will be the same as before, but now the complex frequency will be -2 plus J4. This will be my complex frequency. Now what about this one? My signal is cosine omega t. Well, again, from the lecture you should know that you are able to write a cosine of omega t in this form. And when I break this into a sum of two complex exponentials, I can identify that this first exponential has the complex amplitude of 1/2 and the complex frequency is j omega. This second complex exponential has the complex amplitude of 1/2 and the complex frequency is minus j omega. Okay, now let's take a look at something a bit more complicated. Here I have a damped sine, and I would like to express that as complex exponentials. Well, I will start with this sine, which I know I can express in this form. That is what I showed you during the lecture. Now what I can do is to break this exponential into the product of these two exponentials, and I can break this exponential into the product of these two exponentials. And also I can distribute this multiplication. That will give me this expression. In this expression, I can combine these two exponentials into this one and these two exponentials into this one. That will give me this expression. In this expression, I could almost identify two complex exponentials. This would be the first one and this would be the second one. What I definitely can do is to identify that this is the complex frequency of the first complex exponential and this is the complex frequency of the second exponential. What I still could have problems with is to identify what is the magnitude and phase of this complex amplitude and this complex amplitude. If I really do like my complex amplitudes in the polar form, I need to make some further adjustments. What I need to do is to realize that 1/j I can write as e to the minus j times pi over 2. So this expression I can write like this, and this entire complex amplitude I can write like this. And when I combine these two exponentials, this will be my complex amplitude. The same thing I can do here. This complex amplitude I can express in this form. And when I use this form and this form, I can write this expression like this. And here I can identify those complex frequencies and complex amplitudes now very nicely in the form where I have separated the magnitude and the phase. Now this was the last problem with the complex exponentials. The last thing I want to do here is to take a look at the sampling property of the Dirac delta function. So let's take a look at these integrals and let's try to evaluate them. First, I will integrate from -infinity to +infinity, and I will integrate the multiplication of the cosine and the Dirac delta function. When I plot a cosine and the Dirac delta function, it will look like this, and I will be integrating this from -infinity to +infinity. Now, whatever is the value of the cosine for negative time and whatever is the value of the cosine for positive time, it does not matter because the Dirac delta function is 0 there. The only value that matters is the value of the cosine at time 0. That is where this Dirac delta function will sample this cosine. Thus, the result of this integral will be cosine at time 0, which is equal to 1. Now, this integral is a bit tricky. It's almost the same as this one, but this lower integration limit is now pi. So this integration happens from pi to plus infinity. And the tricky part is that in that interval, the Dirac delta pulse is only 0. This integration interval does not include this Dirac delta pulse, it includes only zeros. Therefore, the result of this integral is 0. Now, this integral. Here I'm integrating from 0 to 2, and I'm integrating the multiplication of an exponential with the Dirac delta pulse, which is time shifted to the position of 1. Here I have it plotted. This is my exponential, and this is the Dirac delta pulse shifted to the position of 1. So when I integrate from 0 to 2, that includes this interval, that will include this Dirac delta pulse, and that I will have the sampling property of the Dirac delta pulse. The values of this exponential for any time less than 1 will not matter because the Dirac delta pulse is 0. The values of this exponential for any time greater than 1 will not matter because that exponential is being multiplied by 0. The only value that will matter is the one which multiplies the Dirac delta pulse at time 1. Thus, I will have that sampling property of the Dirac delta pulse at time 1, and the result of this integral will be e to the 1, or e. Now, this integral is on the tricky side. I'm integrating the same function, but now the integration interval goes from minus infinity to 0. It goes from minus infinity to 0. This integration integral does not include this Dirac delta pulse. Therefore, this exponential is being multiplied by zeros only. Consequently, the result of this integral is 0.